Let's talk a bit about heat. Heat is the exchange of thermal energy. And heat exchange is going to happen when the system and surroundings have a difference in temperature. Now, temperature is the measure of thermal energy within a sample. And as you know from living, heat flows from things with high temperature to those with low temperature until they both reach the same temperature, which is called thermal equilibrium. So we're going to use temperature to measure heat moving between two systems, or a system and surroundings. Okay, one way to think about that is when a system absorbs heat, its temperature is going to increase. And that increase in temperature is directly proportional to the amount of heat absorbed. But we need a proportionality constant because not all things absorb heat in the same way. So that proportionality constant is called the heat capacity. And the units are either joules per degree Celsius or joules per Kelvin. And our heat is the heat capacity of whatever object or liquid we're looking at times that change in temperature. So the larger the heat capacity of the object, the smaller the temperature rise will be for a given amount of heat. One way to think about this is on a sunny, warm day, you know that if you walk in sand, your feet are going to get rather warm rather quickly. Sand has a fairly low heat capacity, and so its temperature increases quite a bit with the heat from the sun on it. Whereas water has a higher heat capacity, so if you walk in, say, Lake Michigan, the heat from the sun does not warm it up all that much. Here's what I was talking about. The heat capacity is going to depend on the material, that's the second point down here, and the amount of matter, which is usually measured by mass. So 200 grams of water is going to require twice as much heat to raise its temperature as 100 grams of water does. So if you have a pot on the stove, you fill one pot halfway full and an identical pot all the way full, they're not going to boil at the same time because it's dependent on how much water there is. And then here's my sand example. 1,000 grams of joules of heat energy will raise the temperature of 100 grams of sand by 12 degrees, 100 grams of water only by 2.4 degrees. So the sand gets hotter faster than the water does, even though they're absorbing the same amount of heat. Specific heat capacity is the measure of a substance's intrinsic ability to absorb heat. It's defined as the amount of heat energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. And the what we use for it is C sub S, and the units are joules per gram degree Celsius. You can also, sometimes you'll run across molar heat capacity. That's the amount of heat required to raise the temperature of 1 mole of a substance 1 degree Celsius. And those units would be joules per mole degree Celsius. And you can see here, water has a high heat capacity compared to everything else in this list. And that high heat capacity of water is essential for life on this planet because the large amount of water on the earth is what's absorbing heat and keeps the temperature on earth cooler. It's also, if you go out to the beach in the summer, the temperature is cooler at the beach than it is inland a bit. That's because the water is acting kind of as a heat sink and the air around it isn't warming up as much. Water can also be used as a coolant because it can absorb a lot of heat, remove it from mechanical parts, keep them from overheating. You can also use it to transfer heat to something else because it's a fluid and it will flow. So the heat capacity is proportional to its mass and the specific heat of the material. So we can calculate the amount of heat absorbed by an object if we know its mass, it's the specific heat of the material it's made out of, and the temperature change of the object. So overall, our heat is mass times specific heat times our temperature change. Let's use that equation. How much heat is absorbed by a copper penny with a mass of 3.10 grams whose temperature rises from -8 degrees Celsius to 37 degrees Celsius? We know that our heat is our mass times our specific heat capacity times our change in temperature. So our mass is 3.10 grams. Our specific heat we can look up in table 6.4. For copper, it is 0.385 joules per gram degrees Celsius. And our change in temperature is always the final 37 minus our initial -8, which gets us a temperature change of 45 degrees Celsius. Then we can multiply all of that out, and we get a Q value of 53.7 joules. The other thing to check is the sign. It is a positive 53.7 because the penny is absorbing the heat from the surroundings. One more practice problem for you. A 3.54 gram piece of aluminum is heated to 96.2 degrees Celsius and allowed to cool to room temperature, 22.5 degrees Celsius. Calculate the heat in kilojoules associated with the cooling process. The specific heat of aluminum is 9.903 joules per gram times Kelvin. So our Q is mass times the specific heat times our change in temperature. So our Q is going to be 3.54 grams times 9.903 joules per gram Kelvin. Now here, because we're doing a difference, it doesn't matter if we're in Kelvin or Celsius. If it makes you feel better, you can switch over to Kelvin, but either way, you're just looking at the difference. And because the degrees in Celsius and Kelvin are the same distance apart, it doesn't matter. So our final temperature is 22.5 minus 96.2. So our delta T is negative 73.7 degrees Celsius or Kelvin. The units are the same. So our Q overall is going to be negative 236 joules, because our units here were in joules and the question asks for kilojoules. So our answer is negative 0.236 kilojoules, which is letter D.